This is the 10th video in a series devoted to differential equations. In our last video, we just started looking at second order differential equations. I should say second order linear differential equations. And today we're going to look at a very special case of second order homogeneous linear differential equations. And those are the such differential equations with constant coefficients. So if you recall last time, our coefficients could be functions of x, but now they're just constants. So that means that the general shape of the differential equation which we will solve today is a y double prime plus by prime plus cy equals 0, where a, b, and c are real numbers. And in fact, unlike what we saw last time, where we really weren't able to solve any differential equations, we could like verify a solution, or we had some theorems to say that a solution was unique. Today we're going to have a constructive way to solve all such differential equations. Okay, so I'd like to start with a leading example, and that leading example is y double prime minus 5y prime plus 6y equals 0. Great. Now I'm going to do a trick here, and that trick really isn't anything. I'm going to define an operator d, and that operator attacks the function y and turns it into y prime. So that means if we square the operator d and attack the function y, we get y double prime. So this is just the derivative operator. Maybe you would want to say d is d by dx, but it's a little cleaner just to use this capital D here. But like I said, you could write d as the operator d by dx. Now what I'll do is rewrite this differential equation with the d operator. So that'll be d squared y minus 5 dy and then plus 6 times y equals 0. But now let's recall that differential operators are linear transformations. That means that we can factor this y, thought of as a vector in a vector space of functions, out of the right-hand side of this kind of whole operator. That's going to give us something like this. We'll have the operator d squared minus 5d plus 6 attacking the function y, like that. Now, like I said, we know that the d operator is a linear transformation on the vector space of continuous functions. I guess I should say smooth functions. So that means that d squared is also a linear transformation because it's a composition of two linear transformations. And we read the number 6 as 6 times the identity linear transformation. And then the set of, or the vector space of linear transformations is closed undertaking linear combinations, and that's what we've done here. We've taken a combination of d squared, d, and the identity linear transformation. Okay, so anyway, this is what we're left with. This is our new version of our original differential equation. But if we look at this, this looks like a polynomial which we could definitely factor. And indeed we can factor it. This factor is as d minus 3 times d minus 2. And then that's on the function y. But now we're going to go through a way to solve this differential equation, and we're going to do that via a substitution. And the substitution that we'll make will turn this into really two first order differential equations, both of which we know how to solve. So I'm going to take all of this that I'm putting a green box around, and I'm going to set that equal to z. So that gives me a new differential equation, d minus 3 times z equals 0. Where, of course, z is equal to d minus 2 on the function y. But now let's rewrite this back in our kind of canonical format of a differential equation as z prime minus 3z equals 0, or in other words, z prime equals 3z. Now that's a separable differential equation, but doing separation of variables on this differential equation is quite a bit overkill. And that's because what we have is a function that when we take its derivative, it essentially stays the same except it picks up a multiplier of 3. And I think the best way to solve this is just to go through the catalog of functions in your brain and remember that this looks like we've taken the derivative of an exponential function. And here we would get z is equal to some constant, I'll call it c1, times e to the 3x. Okay, so we've solved for z here. But notice that z was also written in terms of y via this d minus 2 operator on y. So that gives us a second differential equation. So let's move over here and see what we have. So like I said, equating these two z's, we get d minus 2 operating on y. That's the same thing as y prime minus 2y equals c1 e to the 3x. So c1 e to the 3x. Great. And now that's a first order linear differential equation. We've got a standard formula for first order linear differential equations. Now you could just plug this into that standard formula. But instead of doing that, I'm going to multiply by an integrating factor just because I think it's a little cleaner of a solution. And that integrating factor is motivated by the fact that we have a minus 2 here. And what do you take the derivative of to get a minus 2 out front? Well, you take the derivative of something like e to the minus 2x. So I'll multiply this whole thing by e to the minus 2x. That'll leave me with e to the minus 2x times y prime minus 2 times e to the minus 2x times y equals c1 e to the x. But now if we look carefully at this left-hand side, it looks like we've taken the derivative of a product of functions. Those functions being e to the minus 2x and the other function being y. So that means we can take this left-hand side and rewrite it as e to the minus 2x times y all prime. And like I said before, that's equal to c1 e to the x. So just to reiterate, if we take the derivative of this with the product rule, we most definitely get this line that's right above, so that's okay. And I guess I should underscore one more time that we could have just looked at this kind of original first order differential equation here and used our standard formula for solving a first order linear differential equation. But I think this is a little more of a aesthetic way to solve it. Okay, so anyway, now we can take the antiderivative of both sides. That'll give us e to the minus 2x times y equals c1 e to the x plus c2. Nothing changes on the right-hand side with the e to the x term because the antiderivative of the e to the x is e to the x, but we get a constant of integration from taking that antiderivative. Now we can multiply through and we'll end up with y equals c1 e to the 3x plus c2 e to the 2x. And that would be our final solution. And we know that since we have a second order differential equation, we should have a solution that has two arbitrary constants built in from stuff that we saw in the previous video. Okay, so let's do a little bit of a summary on this example and have that lead us towards a general way to solve at least part of these types of problems. So let's summarize what we saw with our leading example. So that was the differential equation y double prime minus 5y prime plus 6y equals 0. We found that its most general solution was y equals c1 e to the 3x plus c2 e to the 2x. But along the way, we factored like a polynomial form of some sort of linear transformation. So maybe that polynomial underpinning the whole thing is important, and in fact it is. And we'll call that the associated polynomial to this differential equation. So we can put that in terms of this data up here. So notice that R1, which is 2, and R2, which is 3, I'm naming R1 and R2 here, are roots of this associated polynomial r squared minus 5r plus 6 equals 0, where I replaced y double prime essentially with r squared, y prime with r, and y with just maybe r to the 0 or the number 1. So it turns out translating this differential equation into a quadratic polynomial and then finding its roots tells us the form of the solution to the differential equation. Notice that these exponentials, e to the 3x and e to the 2x, are directly related to these two roots here. So I think that's a nice structure that we have for this differential equation. And in fact, this is essentially how you solve 1/3 of the differential equations that are of this form. And we'll have a big theorem up here in just a second. But before we do that, let's look at the following claim. So if r satisfies the following polynomial equation, ar squared plus br plus c equals 0, then y equals c1 e to the rx is a solution to the differential equation a y double prime plus b y prime plus cy equals 0. And we can check this just by direct calculation. So we can first calculate y prime. We'll see that that is r times c1 times e to the rx. We can calculate y double prime. We'll see that that is r squared times c1 times e to the rx just by derivative rules. Now we can look at the right or left-hand side of this differential equation. Ay double prime plus by prime plus cy. And we'll see that that turns into r squared c1 e to the rx. For a y double prime, I need an a out front. And then plus b times r times c1 e to the rx. That's like my by prime. And then plus c times c1 e to the rx. That's like my c times y. But I can factor a bunch out of this. I can factor a c1 e to the rx. And I'm left with ar squared plus br plus c. But ar squared plus br plus c was 0, so that means this equals 0. So now reading from this extreme left to right-hand side, we see that this indeed is a solution to our differential equation. So it looks like if we can find a polynomial associated to these types of second-order differential equations, then we know a solution. And in fact, if we can find both roots to this polynomial, then we can write down the most general solution as described by this example. So let's get the first part of our big theorem on the board over here and then do another example or two. So summarizing what we've done so far, we have the first part of the following theorem. So the differential equation ay double prime plus by prime plus cy equals 0, where a, b, and c are real numbers, has a general solution given by y equals c1 e to the r1x plus c2 e to the r2x if r1 and r2 are distinct real roots of the associated polynomial. So that'll be ar squared plus br plus c equals 0. So essentially what's going on here is we're able to transport this second order linear differential equation with constant coefficients to finding the roots of a polynomial. So a differential equations problem to like a high school algebra problem. So that's pretty nice. So let's do a couple of examples just to make sure we know what's going on before we start adding to this theorem. So for our first example, we'll look at y double prime minus y prime minus 12y equals 0. So that tells us to look at the associated polynomial r squared minus r minus 12 equals 0, but this thing factors. It factors like r minus 4 times r plus 3 equals 0. So look at that. We have two distinct real roots for this polynomial. Those are 4 and negative 3. So since this thing has roots 4 and -3, we can easily write down our general solution. That'll be c1 e to the 4x plus c2 e to the -3x, where c1 and c2 are arbitrary constants. Now I should point out that those arbitrary constants can be determined if we have an initial condition. We'll look at some examples with that a bit later. Okay, now let's look at this one. So we've got 6y double prime minus y prime minus 2y equals 0. So that tells us we should look at the associated polynomial 6r squared minus r minus 2 equals 0. So that factors as well. That indeed factors like 2r plus 1 and then 3r minus 2 equals 0. That also has distinct real roots. We've got a root of r equals 1/2 and we have another one of r equals 2/3. So that tells us we have a general solution of y equals c1 e to the x over 2 plus c2 e to the 2x over 3. And that should have been minus x over 2. So that's our general solution in this case, where again, c1 and c2 are arbitrary constants. Now, you might say, well, what if this polynomial doesn't have distinct real roots, but it has a single real root? That means a double root. And that's what we'll look at now. So now we're going to look at the following question. What if our associated polynomial, ar squared plus br plus c equals 0, has a single repeated real root, which we'll call r1? But if this thing has a single repeated real root, that tells us it factors a certain way. So we have ar squared plus br plus c factors as a times r minus r1 quantity squared. And that's just by the definition of a repeated root or a double root. We know that it can't be more than a double root because we have a quadratic equation there. Okay, next up, by multiplying this out, we can relate R1 with A and B. And in fact, what we get is R1 is in fact equal to negative B over 2A. So again, that's what we get for this being a repeated real root. Okay, so what do we know so far? So what we know from the claim that we already proved is that the function y1, which is e to the r1x, is a solution to the differential equation ay double prime plus by prime plus cy equals 0. Let's recall that that claim that we proved didn't have anything to do with those things being distinct roots. It just said that if we had a root to a polynomial, and R1 is most definitely a root to a polynomial, it's just a special type of root. But this means that we can't find the other solution like we did before because the other solution will have a slightly different form. So how can we go about finding the other solution? Well, we can do something that we did in the previous video, and that is calculate the Wronskian two different ways. One way is by the definition, and one way is by Abel's formula for the Wronskian. Okay, so now let's suppose y is the other solution. And like I said, we're going to calculate the Wronskian two different ways. We're going to do it by the definition of the Wronskian, and that is w of x is equal to the determinant of a certain 2 by 2 matrix. And that 2 by 2 matrix has y1, y1 prime here, and y2, y2 prime here. But I'll take y to be y2. So that means I have e to the r1x here, and I have r1 e to the r1x here. That's from y1 and y1 prime. And here I have y and y prime. Again, that's the definition of the Wronskian. Now we can take this derivative and note that we get e to the r1x times y prime minus r1 e to the r1x times y. Okay. Then we can also calculate the Wronskian using Abel's formula. This is something that we calculated in the previous video. We proved Abel's theorem for calculating the Wronskian in the previous video. and that is w of x is equal to the exponential of negative the antiderivative of the function multiplying y prime. But it's only the function multiplying y prime when we scale this, so the coefficient of y double prime is 1. Turns out in this case it's quite easy, that's just going to be b over a. So it's that antiderivative right there. But now let's note from this up here, if b over 2a or negative b over 2a is r1, then that tells us that b over a is negative 2r1, or negative b over a is 2r1. So that means we can replace this minus b over a with 2r1. So that's the nice kind of simplification that we need here. Okay, so here we have the exponential of the antiderivative of 2r1, so that'll be 2r1x. But that's just e to the 2r1x. I just write the exp out when I put integrals in there, just so it's a little bit easier to look at. Okay, nice. So what we did is calculated the definition of the Wronskian, Abel's Wronskian, so that means we can set those two equal to each other. That leaves us e to the r1x times y prime minus r1 e to the r1xy equals e to the 2r1x. And then from here, I'm going to multiply by e to the minus 2r1x to start simplifying this. That'll leave me with e to the minus r1x y prime minus r1 e to the minus r1xy equals the number 1. And I guess I should point out at this stage right here, you could solve this via the standard strategy for a first order linear differential equation, but I think this is a little bit more aesthetically pleasing the way that we're doing it here. And it's always good to keep in mind different methods. I gave you that cookie cutter method for solving first order linear differential equations, but that doesn't really require anything other than just dropping into a formula. So it's nice to kind of see a prettier way to do it if possible. Okay, so now let's notice that this left-hand side looks like we've taken the derivative of something with the product rule. That's because the derivative of e to the minus r1x will be minus r1 times that. So it looks like we have e to the minus r1x times y all prime equals the number 1. Okay, well, I think we could squeeze it in, but since there's some more writing after this, let's bring this right here and then finish off finding a general solution in this special case. So by setting the definition of the Wronskian equal to the Wronskian as calculated from Abel's formula, we found that if y was the other solution to this differential equation, then the following differential equation involving y was satisfied. E to the minus r1x times y all prime equals 1. Now we can take the antiderivative of both sides. That'll leave us with e to the minus r1x times y equals x plus some constant. But I'll leave the constant out because if you notice, multiplying through by e to the minus r1x to that constant will achieve the solution that we already know. So there's no point in doing that. So just doing it like that is kind of enough for our purposes. Okay, so that tells us y equals x times e to the r1x after multiplying through by e to the r1x to solve for y. Okay, great. So look, we've got this solution right here, which we called y1. Then we have this solution down here that we called y. We could put them in a Wronskian and see that they're linearly independent. I won't do that. I'll let you guys do that. But what you'll see is that they are linearly independent. That means they form a fundamental set of solutions for this special case, which means our general solution can be written as C1 plus C2 times x times e to the r1x, which we get just from factoring the e to the r1x out of both of these after taking their linear combination. So this gives us a general formula for the solution to this type of differential equation when its associated polynomial has a double root. Okay, so let's look at a couple of examples of that and add that case to our big theorem. So we've got our next case added to our big theorem, and that says that this second order linear differential equation with constant coefficients has a general solution of y equals c1 plus c2 times x times e to the r1x if r1 is a double root of the associated polynomial ar squared plus br plus c equals 0. Now let's do a quick example of that. So we've got this differential equation, which is y double prime minus 2y prime plus y equals 0. Here we've got some initial conditions. Y of 0 is 1 and y prime of 0 is 2. So that's nice. We're going to have a little bit of extra work to do. So notice the associated polynomial is r squared minus 2r plus 1. That factors as r minus 1 squared. So that tells us that we have a double root, which is r1 equals 1. Okay, so that means our general solution before we look at our initial conditions goes like this. We have y equals c1 plus c2 times x times e to the x. It's e to the 1 times x. Okay, now let's calculate the first derivative, as that will be useful for this second initial condition. So in order to take this derivative, we'll need to use the product rule. So we'll first have c2 times e to the x. That's from taking the derivative of this linear polynomial, and then plus c1 plus c2 times x e to the x. That's from taking the derivative of e to the x. Okay. Now let's notice that y of 0, on the one hand it's equal to 1 because that's our initial condition. On the other hand it's equal to c1. That's because if we evaluate this at 0, the c2 part disappears. So that's nice. We immediately know that c1 is equal to 1. We have determined one of our undetermined constants. Now let's calculate y prime of 0. So on the one hand, it's 2 because that's given. On the other hand, it's something like c2 plus c1. Just reading this off. E to the 0 is 1. Plugging in x equals 0 gives us 0 for the coefficient of c2 in the other term. So that's supposed to be equal to 2, but we already know that c1 is 1, so that tells us that c2 is also equal to 1. Great. So that means we can write down our final solution, which is 1 plus x times e to the x. Great. So we've got a final solution to this differential equation. Now we've got one more case to look at here, and that would be the case where the associated polynomial doesn't have any real solutions. But let's recall, if it doesn't have any real solutions, then it has complex conjugate solutions. So like I said, that is the third big case to add to this theorem. So let's look at that. So finishing off the cases of this theorem, we need to look at the following question. And that is, what if the polynomial associated to our differential equation has complex conjugate solutions? And those are non-real complex conjugate solutions. Because of course, if you have a double real root, then those are also complex conjugates of each other. So these are non-real complex conjugate solutions. So that means we could call them R1 and R2 as lambda plus I mu and lambda minus I mu, where lambda and mu are real numbers. That's just the definition of these two things being complex conjugates of each other. But that implies that we have the following factorization of our polynomial. So we have AR squared plus BR plus C factors as A times R minus R1, which is lambda plus I mu, and then R minus R2, which is lambda minus I mu. Great. But now let's multiply that out to see what we get in terms of lambda and mu when this whole thing is expanded. Notice, since we know A, B, and C are real numbers, all the stuff with I should cancel out. And in fact, it will. So we'll get A, and then we'll have R squared from R times R. But notice in the cross term, the imaginary part will cancel. That's because we've got negative lambda plus I mu minus lambda minus I mu. So the I mu parts cancel, leaving us with 2 lambda times r. So again, that's for the cross terms. And then what do we get for the constant term? Well, we get lambda plus I mu times lambda minus I mu. That ends up being lambda squared plus mu squared, just by kind of a difference of squares involving that complex number. Okay, great. So what does that tell us? That tells us if y is a solution of ay double prime plus by prime plus cy equals 0, then it's a solution of, let's see, y double prime minus 2 lambda y prime plus lambda squared plus mu squared times y equals 0. And that's because these two differential equations have essentially the same associated polynomial. They're just off by a constant multiple of a. But this constant multiple of a will not change the solutions to the differential equation. So now let's hone in on this format for our differential equation. That'll be more useful for where we're going. Let's also hone in that the real part of both of the roots is equal to lambda. And we know that if the roots are all real, then the solution is given by the exponential function defined by that root, e to the r1x, e to the r2x, r1 and r2 are roots. So I think that, along with the fact that these lambdas are the real parts of these roots, motivates the following substitution. So here, let's write down this substitution. So I'll call it maybe y equals e to the lambda x times z, where z is some function that we have to determine. So again, that's motivated by the fact that these are the real parts of these roots and what we've seen already over here. So hopefully this will have some sort of simplification effect. Okay, so let's notice that if y is equal to e to the lambda x times z, where z is some function, then y prime is equal to e to the lambda x times z prime plus lambda e to the lambda x times z, just by taking the derivative using the product rule. And then furthermore, y double prime is equal to e to the lambda x times z double prime plus 2 lambda e to the lambda x times z plus lambda squared e to the lambda x times z. So there I just took the derivative, carefully taking the product rule at each step. Okay, so now let's plug this version of y, this version of y prime, and this version of y double prime into our differential equation right here, which is equivalent to our starting differential equation, and see what we get and see if anything cancels. So let's first note that e to the lambda z can be factored out of every term that occurs here. So let's go ahead and factor that out. So e to the lambda x, I should say. And then what do we have left over? So our y double prime will have a z double prime plus 2 lambda z prime plus lambda squared times z. So that's left over from my y double prime. Then next up, I have minus 2 lambda times y prime. So that's going to give me a z prime plus lambda times z from this term right here. And then I finally have a lambda squared plus mu squared times a z left over. So again, that is what we get from doing this substitution on our starting differential equation. It turns it into this differential equation. And I guess I should say put this equals 0. Now let's see if anything cancels out, and stuff will cancel out, which is quite nice. So let's notice that here we have a plus 2 lambda z prime, and here we have a minus 2 lambda z prime. So that means this thing right here will cancel with this thing right here. So cool. Then we have a lambda squared z here, another lambda squared z here, so that builds up to 2 lambda squared z, and then we have minus 2 lambda squared z here. So those will cancel with each other as well. So this and this double up and cancel with this. Okay, so let's see what we're left with. So e to the lambda x is never equal to 0. Real exponentials are never equal to 0, so we don't need that in there. And all we're left with is z double prime plus mu squared times z equals 0. Okay, so let's summarize what we have at the top board and then get a general solution for this type of differential equation. Let's see what we've done so far. So we showed that substituting y equals e to the lambda x times z into our differential equation ay double prime plus by prime plus cy equals 0, where its associated polynomial had complex conjugate non-real solutions, reduced to the following quite a bit simpler differential equation involving z. And that was z double prime plus mu squared times z equals 0. But notice that that's the same thing as saying that z double prime is equal to minus mu squared times z. Now we're going to do something that a lot of people don't like, but is used a lot of times in math, and that is scrolling through the functions that we have in our brains and trying to guess a solution for this, or really guess some sort of general solution that depends on two functions. So what we're doing is essentially looking for a function so that when we take its second derivative, we get negative what we started with, and we pick up some sort of number squared. So let's say that mu is equal to 1 and we were just looking for a function that when we took its derivative twice, we got negative what we started with. Well, cosine and sine would work. And then we can work the mu in there by composing the mu inside of the cosine and sine function. So through all of that exploratory thinking, we get that z has a general form of c1 times cosine of mu x plus c2 times sine of mu x. So again, take the derivative of cosine twice, you'll get back to a negative cosine, but each time you pick up a mu along the way. So that gives us a minus mu squared. Same thing for sine. But let's notice that z was not the function we were trying to solve for, it was y, which is e to the lambda x times z. But what we have now is sufficient to write down our general formula for y, which will be e to the lambda x times the quantity c1 cos mu x plus c2 sine mu x. Okay, so let's add that to our theorem over here and look at an example. So we've rounded out our big theorem, and that says that our differential equation has a general solution given by y equals e to the lambda x times the quantity c1 cosine mu x plus c2 sine mu x if lambda plus or minus mu times I are non-real roots, so they're complex conjugate non-real roots of our associated polynomial equation ar squared plus br plus c equals 0. So these three things together gives us the power to solve any such differential equation. Okay, so let's look at an example that illustrates this third case. So we've got y double prime plus 6y prime plus 10y equals 0. We've got an initial condition over there too. So that means we need to look at the polynomial equation r squared plus 6r plus 10 equals 0. So you can check this, but it won't really factor. Well, it will factor using complex numbers, but the easiest way to get at that is with the quadratic formula. So we'll know r will be negative b, so that's minus 6, plus minus the square root of b squared, that's 36, minus 4ac, so that's minus 40, and then this is all over 2. Okay, good. So let's notice that 36 minus 40 is equal to -4. You take the square root, you get 2i. So this is going to be -6 plus minus 2i over 2. In other words, -3 plus or minus I. So that means in our language over there, lambda will be equal to 3, and then mu will be equal to 1, because 1 is the coefficient of the real or the imaginary part. Okay, so that means our general solution is e to the minus 3x, and then we'll have c1 cosine x plus c2 sine x. Now we can take the derivative of that because we'll need that for our initial condition. So notice that the derivative here will be minus 3 e to the minus 3x, and then we'll have c1 cos x plus c2 sine x. So that's from taking the derivative of the exponential part, and then plus e to the minus 3x times the derivative of the trigonometric part. So that'll be minus c1 sine x plus c2 cosine x. Great. Now let's impose these initial conditions. So y evaluated at 0. So e to the 0 is 1, cosine of 0 is 1, sine of 0 is 0, so that gives us c1. But c1 is meant to be equal to 2. So immediately we know the value of c1. And now let's plug in y prime of 0. So we'll get -3 for this first term. We'll get c1 for this first term as well. So c1 is 2, so that gives us -6. And then for this second term, we'll have a 1 here, a 0 here, and a c2 here. So that'll be plus c2. That's meant to be equal to -1. So that means that c2 is equal to 5. So now we know both of our kind of arbitrary constants. They're not arbitrary anymore. We've got c2 is 2 and c1 is 2 and c2 is 5. So that means we can erase these two things, and we'll have a 2 here and a 5 here, and that would be the final solution to this initial value problem. Okay, I'll leave you guys with some warm-up problems. So I've got 3 warm-up problems for you, and you probably guessed that they illustrate these 3 parts of our big theorem. This theorem is super important for solving these types of differential equations. It's probably useful to commit it to memory. I'm not a big fan of like memorizing stuff, but if you do enough of these, you'll have it in your memory already. Okay, so the first one is 2y double prime plus 7y prime minus 15y equals 0. And then we have y evaluated at 0 is -2 and y prime evaluated at 0 is 5. So that's our first warm up. Our second is 9y double prime plus 24y prime plus 16y equals 0. We've got y of 0 is 3 and y prime of 0 is 1. Then finally, we have y double prime minus 6y prime plus 13y is 0. Our initial conditions are y of 0 is 1 and y prime of 0 is -1. And that's a good place to stop.